In this next module, we are going to take a look at approximate techniques. There are two basic situations where we have different classes of approaches. One of them is for gravity load effects, one of them is for lateral load effects. In the old days, we would actually complete design and analysis using some of these approximate techniques. These days we do it for two basic reasons, one of which is to quality control the data entry for our computer models and try to get approximate answers that will tell us whether or not we've likely or reasonably entered data into the computer. The other thing is that these approximate approaches are based upon real behavior. So as we understand the approximate approaches better, we'll understand and develop better intuition about how structures are going to respond. Right? So the portal method is a technique for lateral load analysis. We are not going to go into the cantilever method, which is a method for tall buildings, and instead we'll just focus on more conventionally relatively shorter buildings, so things that are less than 10 stories tall. And then the gravity load analysis approach too is going to be one that's useful for both beams and frame kind of situations. Right now, in both of the approaches here, the key thing is assuming locations of inflection points, and the better that we do at guessing where the location of those are, where the internal moment is zero, then the better then the approximation will be. And indeed, in some cases, we can get that exactly correct, and so there won't be an approximation at all. But typically we'll just guess where those are located. And then for lateral load analysis, we oftentimes then need to also make an assumption about the relative stiffness of columns and about how those lateral load effects are distributed amongst those various columns. So let's look at several extreme examples that provide a framework then later for us to go and do some numerical analysis. All right, so one of the common or extreme situations is what we might call a cantilever column. That's going to happen, say, in a moment resisting frame where the I over L of the beam compared to the I over the L of the column is such that the beam offers little to no stiffness, as though it were a hinge up at the top. In other words, the column is much stiffer than the beam. Now that doesn't generally happen, but it is one of the extremes that we might be considering. And when that might be the case, or help us to provide a bound for the response of that column, then we might be thinking about the shear that is imposed on the beam. It's going to then respond in a fashion that is similar to the deflected shape as shown, and this resulting displacement delta then is going to be related to V through V equal 3EI over L cubed times delta. And so this will be an important sort of stiffness value. That's what effectively this little thing is here. Force equals K times the deformation or displacement. And that's very useful in earthquake engineering, that we might be looking at a system if we believe that the beam is relatively flexible compared to the column. That usually happens because the length of the beam is so much longer than, say, the column. And it may be that we need to look at some, not I over L, but I over L squared, L cubed, the kind of thing that you begin to see here is one of the ways that we might begin to look at this comparison. In other words, it's not just a one-dimensional comparison. We might have to look at a range of things before we believe that we have this kind of situation. Right? Another one would be a column with a hinge at the top. That's effectively what we have here, is a little hinge at the top, no moment at the top. But now we don't have any sway. Now this one happens more in the development of a lot of other models, and typically what we're interested in there is what happens when we impose a moment here. And then what you're going to find out is that the deflected shape would look like so. It'd be a reverse curve, and we'll derive at some other time that the moment that happens at the far end, or the fixed end at that far end, is going to turn out to be half of the moment that was imposed here. And when that happens, the inflection point location would be right at the 1/3. How the heck do I know that? Well, come in, let's draw the moment diagram real quick that goes with this. we've got the moment at one end. That's going to be M. There's your M. And then it's going to the other side at the far end at half. And there's your key, right? That there's a 2-to-1 ratio. And so that means, and I don't really care which one's positive, which one's negative. The most important thing is that they show up on the opposite sides, right? The arrow is pointing towards where the compression side is located. And that means with that 2-to-1 ratio that that inflection point is going to be at the 1/3 height in that away from the fixed end. That's an important key thing. Right, so notice inflection point on the top one is right there at the top. That's where the moment is going to be 0 there. And there again, if we would like, we could draw the moment diagram that goes with that, and it's just going to linearly increase over the height of the column and would just be equal to V times H, or L. I guess I've got it written over here, so make that V times L of the column. Right, so that's two extreme cases, and then let's look at a third one that happens if the I over L of the beam, instead of being a lot less than that from the column, let's say it's a lot more than that from the column. So it is much stiffer than the column is. And so when the structure now sways, what's going to happen is that we get no rotation up at the top of the column, and of course there's going to have to be a moment that's associated with that holds that from having rotation, just like there's a moment down here at the base. And so those moments will be equal and opposite to each other in that particular situation. Of course there's going to have to be, you know, a force to move that over as well. And let's just, for consistency, draw the moment diagram again. And you got then, in this case now the moment diagram will look the other way. And of course that zero moment, or the inflection point, is going to be in the midpoint in that instance. And one last little piece before we charge off there. If that's V and it moves over by delta, what you'll find out there is that V would equal 12E I over L cubed times delta. That this is 4 times as stiff as this cantilever, which sort of makes sense when you regard that this little portion from here to here is very much like a little cantilever column, and there's an L over 2 business that gets worked into here, and you end up with then 12EI over L cubed instead of the 3EI over L cubed that we have up at the top. Again, this will, in earthquake engineering, this will be one of your most common situations you work with moment resisting frames. This gives us a range, though, of 3 typical kinds of situations that we might have with columns and how they're connected to something at their top, whether it provides flexural resistance. Right here, this one does. This one does not, but there's no sway. This one does not, but it does have sway. Those range of effects are going to turn out to be very important to us as we start to approach these approximate techniques.